Now, so just as a curiosity, or maybe just a comment, thermodiffusive instability are essentially a competing effect between two things that diffuse. In this case, heat and mass. But most likely, if you imagine of a system that, let's say, even under isothermal condition, you have two species that diffuse at different rate and try to mix, most likely you're going to get also a similar type of instability because there's a fighting between the two diffusion into each other. Of course, if they go in one direction, they don't fight. So, in fact, it was described for a chemical system years ago by Turing. I don't know if you know that name. Turing is one of the inventors of computers. And there's even a movie that talk about his life and so on during the war. And so it's interesting that he wrote a paper that has quite an implication on combustion system, even though it wasn't a combustion paper at the time. So anyway, that was just a side comment. So the combined effect, and I started with a bit of historical comment, some of which I already mentioned a little earlier. So Markstein was intrigued by this instability of Darrow and Landau, and so he went by assuming a dependence of flame speed on flame curvature, using a phenomenological parameter that we now call the Markstein length. And he introduced a flame speed which is not constant. In other words, different segments of the flame propagate differently based on the curvature. And he was able to experimentally describe a variety of these cellular observation. The more advanced asymptotic method, which I discussed during the week, were done using a multi-scale approach, and they were done to treat the flame as a boundary layer or as a thin layer where the effect of thermodiffusive effect are inside the flame and they are affecting the flame speed. And so when we wrote earlier this week, a flame speed depend on flame stretch. Stretch was written here, curvature, and if you like, strain. Then the coefficient here that we derive is essentially like the Markstein length. In fact, we refer to it as a Markstein length in tribute to Markstein. As you not see, but I think I'm not going to show an analysis, but more discuss the result. If you redo the Darrow-Landau analysis and account for effect of stretch, which enter as a coefficient that is of the order of the flame thickness and depend on the effective Lewis number. And remember, the effective Lewis number was some kind of an average Lewis number of the fuel and oxidizer. So the analysis is not a single component, but even have effect of equivalence ratio in it. The effective Lewis number is more heavily dependent on the deficient component. But anyway, there is an expression for it, so it depends on that. Then one get a correction to the Darrow-Landau result. And clearly, the expansion will be the next term in the expansion, which turned out to be a k square as opposed to k. Remember that the Darrow-Landau is in fact a long wave instability because it assumes that the disturbances are long compared to the zero thickness of the flame. And here also they are long compared to the LF thickness of the flame. The derivation was done independently in three places, differently, and lead to the same answer, which really greatly strengthened the answer because it's quite a an elaborate calculation. Just if you're interested, Clavin and his student Pelcet have that led to the approach that they linearize the equation and examine it on two scales. One scale is the diffusion scale, the other scale is the hydrodynamic scale. And since it's a linearized problem, they were able to derive the dispersion relation that is described here. I describe it in terms of the notation that I have used this week, but the notation in those papers are a little different, and have to be careful when you compare. Recently, someone told me, oh, not about this relation, but something related to combustion, that sigma, I said something like sigma -1 is small. He said, no, but it's not what's in the paper. But I define sigma as unburned versus burn, and what he was referring to is the sigma burn versus unburned. It makes a difference what's what. So anyway, this is one. Frankel and Sivashinsky did something slightly different. They say, well, if the Darry lambda is proportional to k, we're going to look as a perturbation to obtain k squared. So they were looking at the k as the small parameter. When you do this, of course, what happened is that in addition to the equation that you obtain, we describe within the flame, there is a far field, and you have to address the far field. What is the far field? The far field is the hydrodynamic zones. And the last approach was done differently. What we were thinking is we are going to derive first a model, which I described to you earlier this week, of a thin flame, irrespective, not disturbing, not linearize the equation first, but first obtaining the general model. The advantage has been that we can also use this equation to describe spherical flames, which are not a perturbation of a plane. So our equation were able to describe that. And two, they were nonlinear. So in principle, we can also, not only in principle, I'll show you also a result that we describe the nonlinear effect as well. So, but as I said, for the stability problem, we have a term which is proportional to k squared. In other words, it depends on this coefficient b, if it's positive or negative, that you will be able to get more stabilizing effects or not, okay? Now, before we discuss the detail, let's see what this b included. So, in fact, it included three terms. In other words, in the derivation, it was not just a b, it was a long expression that included three effects, and you can identify them. The first one resulted from heat conduction, was this coefficient B1. Now, heat conduction, the temperature spread, causes spread of the temperature, and so it has a stabilizing influence typically. And so that's what it is. In fact, it's negative, and so indeed it was a stabilizing influence. It turned out that the viscous effect, which are entered here through multiplied by the Prandtl number, also have a stabilizing effect, but this was only obtained when the assumption was made that the viscosity of the unburned and burned gas are different. If you assume a constant viscosity, that turn out to be zero, so it has no effect. So viscous effect turned out to have also a stabilizing effect, being negative. The middle term is the one that can change sign because it's multiplied by Lewis number -1, and so it can be stabilizing or destabilizing depend on the sign of Lewis number -1, right? If Lewis number is greater than 1, it's stabilizing. So species diffusion tend to stabilize the waves which are like proportional to k squared, which are the short waves, okay? And when Lewis number is less than 1, then they will destabilize. Of course, Lewis number bigger than 1, less than 1 is not exactly the critical value for the instability or not. It's slightly different because what you need the entire term to be positive or negative. If it's positive, is stabilizing. If it's negative, is destabilizing, just because of the minus sign. So here is the graph. So if B is positive or the Lewis number is above some critical value being slightly less than 1, then the curve that you get here is a parabolic, it's a parabola. The slope here is the slope of the Darry-Landau because it's the long waves, right? And then the short waves are stabilized. Now, all the waves which are shorter than this are stable. When the Lewis number is below, roughly speaking, 1, then the instability, then the Darry-Landau instability is further unstable, okay? And that's the extent, really, that this theory provided. Now, it's interpreted that this become, further unstable because of thermodiffusive effect that tend to destabilize the flame, whereas for Lewis number bigger than 1, thermodiffusive effect tend to stabilize the short waves, and therefore, in principle, the flame is still unstable because there's always a range of wave number that grow. So in order to see a stable flame at least in principle, mathematically, you need to have either an additional effect that eliminates the long waves, or maybe your apparatus, your lab apparatus eliminate long waves. So for example, a burner of a finite size, you cannot have waves or disturbances that are bigger than that. They don't affect the flame. So you are limiting your, it's not always a very convincing argument because you don't want to argue that your results are good only for certain burners, not for others. But it is the result. What can you do? Here is a numerical DNS of hydrogen air flame. And what was seen is that I want to really focus on this part primarily. What you see is similar to the theory. It's not a very good comparison, wasn't made very good comparison, but anyway, it's not important at the moment. It showed that for rich hydrogen air, which would correspond to a Lewis number bigger than 1, because it's a rich hydrogen, you get this, those are the computed value, and you get this parabolic curve as you see. What happened for lean hydrogen air flame? The blue curve presumably is, not presumably, the blue curve is apparently the theory, and what you see, it keep on growing. Now, numerically, of course, you see that there is a bending of the curve, and eventually very short waves are stabilized. The deficiency of the theory, that is, we are unable to, at the current knowledge, the theory does not describe the short wave stability. I mean, it's clear that short enough wave will be eventually stable, but we don't have a description of that from the results that I just showed you earlier. If we take this relation and we set omega equal to 0 to obtain the neutral curve, or the curve that separates stable from unstable, well, it's quite clear, k squared, so if it's equal to 0, you're going to get something over k. So something over k, it's like a hyperbola that is described here, okay? And that's the wave number versus the, say, the Lewis number, deviation from 1. Remember, that curve was the thermodiffusive one that did not include the hydrodynamic effect, and hydrodynamic effects are long waves, so they are here, right? They are this way. So that curve, in a way, showed that it may go here, and indeed, there were some numerics that show that it does. And so what you see here is exactly the asymptotic result, and what you see here are numerical results obtained for a density ratio which is not 1, and these two curves are the thermodiffusive theory that I showed you before. So a lot of information that blend into each other. Now, what is the effect of gravity? Remember that gravity acts on the long waves, okay? And we have seen earlier they stabilize the long wave. So if gravity stabilizes the long waves, this is the Darry-Landau is the dashed line here. This black curve is when G equal to 0. So that's the quadratic term for sufficiently large Lewis number that I have described a minute ago. So in fact, this result is for Lewis number above 1 or above the critical. So the black curve is what we saw before, that the long waves are unstable, but the short one are stabilized by diffusion. Now, gravity stabilizes the long wave. So the red curve, for example, for this value, now don't be confused, that's a gravitational parameter, so gravity, of course, doesn't change on Earth, but the non-dimensional or the ratio here, is G over SL squared. So it tells you that slow flame as opposed to fast flame can affect that parameter. So when that parameter is, let's say, 33, you see the long waves are stabilized, omega is negative, but there is still a range of unstable. But if this is larger, then you get a neutral point, and then it becomes totally negative. So you downward, remember those are downward propagation, G is positive. Downward propagation flame can be totally stable because long waves are stabilized by gravity, short wave by thermodiffusive effect, okay? What happens if it's upward propagation? It's this curve. Again, it's the combined effect of the hydrodynamic, or Darry-Landau, and Rayleigh-Taylor instability. They become more unstable. This is you see now we have 3 parameters in the problem: gravity, Markstein length. Markstein length is essentially the stabilizing influence of diffusion, or Markstein number, Markstein length, and the wave number K. And so you have a hypersurface that separates stable from unstable mode. And this curve here is a neutral curve. As you see, these 4 points show that it's exactly when everything is stable just at the instability threshold. These are curves that show cuts in this graph. In particular, I want to focus on this. If the gravitational parameter is sufficiently large, then you're going to have stable flame, but also for a given G, if the Markstein length is sufficiently large, you're going to get stable flames, okay? Just a comment, flat flame have been observed in a counterflow flame. I said earlier today that nature does not really like or does not promote planar flame, but this was planar flame without effect of strain. So strain clearly has a stabilizing effect, and you see that as you increase the strain, this curve, which is the one that I described a minute ago, just bend back, so there will be a region where the strain will totally stabilize the flame. The discussion is not really complete here because there are other effects due to strain, and I did not bring them into the story. I said that we can also analyze other flame configuration, like spherical flames. And so if you have a spherical flame that you perturb, so you see it perturbed here, and the flame expand as it goes. So the perturbation of the front is going to be R of t, which is the stable surface, the spherical flame, plus a perturbation. But now perturbation should be expressed in spherical coordinates. So spherical coordinates, those are going to be spherical surface harmonics that involve e to the im phi, phi being this angle that spans from 0 to pi, and then theta is the azimuthal angle that go from 0 to 2 pi, and these are Legendre polynomial that describe properly disturbances on a spherical plane. They come from essentially separable solution of Laplace's equation, say. There is a comment that needs to be made here. I started the discussion today by saying when we have discussed stability, we start with an equilibrium. And that equilibrium is perturbed, and we ask what happens as t goes to infinity. An expanding flame is a time-dependent solution. It's not an equilibrium. Okay, you can say it's steadily propagating or something like that, which is not necessarily always the case, but it's not an equilibrium. So what does it mean? So I perturb it. I cannot wait until infinity because the flame is growing as well. So how do I discuss the stability of a time-dependent problem? And that's a question that is raised also in hydrodynamic stability in general. Of course, periodic solution, even though they are time-dependent, you can discuss them because you can say, is there a growth within a period? And you analyze it. But what do you do? So really, you have to comment on two things here. The first one is the perturbation has to grow faster than the flame to be observed experimentally. If the flame, as it expands, it propagates faster than the perturbation that you are imposing, it's not going to be seen in an experiment. So that's the first thing, and that's the reason why we write here the perturbation relative to the flame. In other words, I didn't write R of t plus the perturbation, but the perturbation is relative to the flame. The second thing is we cannot wait until t goes to infinity to determine if the solution have grown or not. So the only thing we are saying is if at a given time momentarily there is a growth or not. So we define instability if the amplitude locally starts to grow. By the way, there is other things discussed in the literature of hydrodynamic stability. For example, freezing a solution at a given time and saying, does that solution grow or not? Which is somehow related to what I said before. That's what they do, for example, in the stability of boundary layer. You know, a boundary layer over a flat plate grow in space, spatially. Now, to analyze the stability of that is not simple. And so what they do, they freeze the profile at a given position. Now it's a given profile, they perturb that profile, and the idea is that the growth is maybe slowly varying, and so you can make some estimate of the growth, the perturbation, as opposed to the growth of the profile. Somewhat it's similar here. So anyway, so actually it's written here, perturbation must go faster than the flame itself, and only we can argue it's a momentary tendency of the perturbation to grow or decay. So the analysis gives us the following result, that the growth rate or the relative growth rate, okay, A is the amplitude, is given by this expression, Note that there is a term here which is proportional to the flame thickness, similar to what we had earlier for a planar flame, and there is a term when that is not accounted for, which turned out to be the equivalent of the hydrodynamic instability or the Ariolando. It's not the same growth rate, but it is the same the nature of that. In fact, because the amplitude change in time, you cannot even make an assumption like we did before that the solution grow exponentially like e to the omega t. Exponential solutions are solution of constant coefficient equation, but not when the coefficient vary in time. So it turned out that they grow algebraically in time, but not exponentially. But that was part of the mathematical analysis. And then this term is proportional to the flame thickness. Again, had three contributions, one related to conduction, one related to mass diffusion, and one for diffusion. And these coefficients, all of them depend on sigma, which is the density ratio on Bern versus Bern, and the wave number n, because perturbations are expressed in terms of n, and the m here is limited by the n. Anyway, those two appear as part. It's like a wave number, if you like. Here is just a descriptive, well, it's not descriptive, it's also the result of the calculation. If you start with a perturbation A normalized to be 1, then different modes meaning different n, shown to first decay and then grow. If the Lewis number is above, let's say, roughly speaking, above 1, whereas if Lewis number is less than 1, perturbation grow immediately. So, in other words, since these are thermodiffusive effect, the idea is, Lewis number less than 1, the idea is that when Lewis number is less than 1, when you ignite the flame at the center, even when it's still of the order of the flame thickness, thermodiffusive instability may develop on the flame. The hydrodynamic theory, or the theory that we have used to derive the stability analysis, is true only if the flame thickness is small compared with that radius. And so it only holds when the flame is not too small, and therefore it only holds for Lewis number bigger than 1. Again, the theory is limited in the sense that we don't have a full description for Lewis number less than 1. As I showed before, we don't have a full stabilization of the short waves. So what we see is that the disturbance first decay and then suddenly start to grow. So there is a critical radius where the instability is first formed. So when the Lewis number is above critical value, and from now on I'll say above 1 and below 1. It's just simply to say the flame remains smooth initially, diffusion exerts stabilizing influences first, and then spontaneously it takes on a cellular appearance, okay? And not only spontaneously it takes on a cellular appearance, spontaneously you have already cells of certain size. It's not that they start going from small, they become larger, okay? And the instability is due to thermal expansion. Primarily it's a combination of Darry-Lambda with stabilizing influence of the short waves. And this is a graph that shows the wave number as a function of the radius, which can be expressed when you normalize it with the flame thickness as a Pickley number. And what it shows is that when the radius is small, the flame is stable. This is stable. And then there is a critical value here. It becomes unstable. And when it becomes unstable, there is a range of modes or of wavelength that are the growing modes, okay? You can see it here. For example, it was for a propane, as I remember. Yeah, it was propane air. In other words, values that correspond to propane air, and we see that when R was 11 millimeters, it was totally stable. Here, one mode started to grow, which corresponds to this nose, and here we are above the critical value. What else can I show? In fact, this was computed also from this calculation. Yeah, two things. Note that this often referred to as a peninsula. I think Derek Bradley at Leeds liked those analytical results, tried to fit his experiment to them, and he used that word, the peninsula of unstable modes. So this peninsula showed that n goes to approximately a constant here, and n is proportional to the radius r here. In fact, it's interesting to note that because this is like the large Beckley number, which means large flame r, it turned out that that limit that you see here, the red dashed curve, it's exactly the dispersion relation of a planar flame. So because when the flame is large, it's locally like planar, and so it tends to that limit. But in fact, it's more interesting to comment the following. When n is approximately constant, you see the wavelength lambda is 2 pi r over n, okay? N is the wave number, that's the wavelength. So if r is approximately a constant, then the growth rate is proportional to r. In other words, the amplitude or the cell size keep on growing as r grow, okay? Whereas here, when n goes like, and those are the long waves, okay? The maximum lambda, because lambda is the inverse of n. Whereas here, n is a proportion to r, so the ratio is approximately constant. So the small cells tend to reach some constant value. The large cells can keep on growing. Apparently, this was also observed experimentally. Just quickly, those are figures of lean hydrocarbon and rich hydrocarbon flame. You see that I put the box red and blue to be systematic with lean and rich, so, or maybe with stable, unstable, I don't know. We'll see. So this is at the same pressure. So we see that the lean flame remained totally spherical, of course, within the window of that apparatus, whereas the rich flame become quite unstable early on at some point here, okay? For this was, okay, still, sorry. So I describe for constant pressure now, same thing, lean and lean, not exactly the same value, but higher, significantly higher pressure. So you see that as a result of the high pressure, the flame become unstable at approximately, you know, for the low pressure it's stable, high pressure. And why is that? Because the flame thickness, which is the parameter that stabilizes or doesn't stabilize, is affected by the pressure. You increase the pressure, LF is smaller, the stabilizing influence are minimal, and so the flame is unstable. So that's, and the same thing here are for hydrogen, but for hydrogen, the rich are stable, the lean are unstable, and if you take the rich at higher pressure, it becomes unstable, okay? Again, a comparison. And this is experimental observation. Now, I had two sets of hydrogen air. I had two sets of video, and I don't remember which one I am showing. One of them, but I'll tell you the two. One of them was done at Aachen, and the other one was done in Orléans. So both show more or less same picture, so I don't know which one is this. So this is one. So you see that hydrogen at the equivalence ratio 1, the flame is stable. This is a higher pressure, and you start seeing the instability. By the way, one has to be careful. Some instability, but they usually are not really related to the cellular structure. They show some cracks on the flame. Can result from the probe that you put in for ignition. So unfortunately, that's the nature of experiments. But this one at higher pressure showed that it become highly unstable right away. Okay. Well, that's a summary of that. This is the comment that I sort of made earlier. In a narrow domain, let's say of length L, then if this is the growth rate of all perturbation, then that limits the ability or long waves longer than of lambda bigger than L are irrelevant. And so you can still observe a stable planar flame if the Markstein length is above some critical value that depend on the length, okay? So in dimensionless form, there will be some critical Markstein lengths, and the larger one are stability, and the smaller one are unstable, or if I express them in terms of the inverse of the Markstein, it's the opposite way. You will see in a minute why. So basically, what we are interested is to analyze now the nonlinear effect. So what we have is the amplitude. It's stable here. This is the inverse of the Markstein, the critical Markstein length. So it's going to be unstable here. And we want to be able to capture the new state that evolved beyond the instability threshold. And the nonlinear theory was done in two ways. First, it was used by a so-called Sivashinsky type equation. Sivashinsky derived an equation which is known as the Michelson-Sivashinsky. Those of you who heard of Kuramoto-Sivashinsky is a different equation. I don't have time to talk about both. But the Michelson-Sivashinsky equation essentially is relevant to this discussion. And it was very useful because it gave some first idea of how to understand the nonlinear effect. But I don't have time to talk about it. I will talk about but it's limited to weak thermal expansion or sigma minus 1 small. I will talk about more the hydrodynamic model, which sigma minus 1 is order 1, like 6, 7, which is real value. But I want to tell you that the validation of results that we have obtained using the hydrodynamic model have captured the correct result when we took numbers that go close to sigma minus 1, which was a very numerical validation of the results. But anyway, again, this is the hydrodynamic model that we are going to use. The main parameter is the Markstein number, but sigma, of course, enter into the picture. Those are the two parameters in that model. And the Markstein lengths appear from the flame speed relation, which is here. It's not trivial mathematical problem to solve because it's a free boundary problem. So you have to solve it and track the flame as it moves. As the flame moves, the density field changes, which is described here. And you have to properly determine the flame speed, which is a quantity that is related to the interface. So it's quite challenging mathematically. Here are just sporadic results, but that's the idea. You start with a highly disturbed flame, and what you see is over time, the small perturbation tend to bunch together, creating larger cells or larger perturbation. And eventually, it collapses into a single shape with a cusp-like or intruding section towards the burn gas. And that flame keep on propagating steadily thereafter at a velocity u. So the long time behavior is that in the 2D, y is minus ut, propagate down here. Down is not gravity, is no gravity here, plus a shape that doesn't change in time. And here are, for example, time-dependent observation of this. Oh, sorry, well. You can see that the cusp-like pointing toward the burn gas exists and propagate thereafter. Doesn't change in shape. And here are a few results that show the dependence on the critical Marsden length or remember the distance, the burner size or the tube size. So when L equal to 1, the M is turned out to be below the critical, which is 0.4. And so you start with a cosine, it flatten out, and it go to a flat flame. You start with L equal to 2, so you are below the critical, and so it's developed into this cusp-like behavior. And here as well, of course, when you are more into the instability, the cusp is sharper and the amplitude is larger. And this is just the flow field that is obtained for two different value of Marsden lengths, therefore two different velocity. See how the flame induces hydrodynamic disturbances in the unburned gas that tend to support or sustain the cusp. I showed you those figures early on this week when I was just showing you examples of propagating flames that are not flat, but they are obtained as a result of the instability. And this is the bifurcation diagram that show in terms of the, I'm sorry, I think this is, well, no, that's correct. I usually plot it as a function of the inverse of Marsden length, but note that M goes this direction. So it's plotted this way, but it's still correct. So when M is below the critical, you obtain the new state that propagate at increasing speed when you are with smaller and smaller. This is a comparison of that bifurcation curves with DNS done at Zurich with Fruzakis and those people. This is for hydrogen air with phi equal to 1. And I have probably some movies, but I'm not going to show them all. Here is one of them. Those are DNS, so it's not the hydrodynamic theory. So you see how they are both agree. And there is a change in the behavior when you change the equivalence ratio or the width of the domain. Here you also establish a single cusp, but after a while it moves, you know, there could be, I don't know the reason, it could be numerical noise that move it, but it keeps on growing. And I think when you start going to lean condition, then it's not quite as you expect, because there are thermodiffusive effects that enter in the picture. And so you're going to see some of them, but it's not a fully comprehensive analysis of this. Actually, the next one is more interesting. This is phi half. So what you're going to see is that when the planar flame becomes unstable, it starts with very small cells, which are the thermodiffusive cells. Not yet. Maybe there is a smaller value. And you still see there is this cusp-like behavior, but not quite. This is the one I was referring to. So you still have this cusp type of behavior, but there are still small cells that get created on the surface due to thermal. And this is really ongoing research, is not completely fully, let's say, understood or fully described. So this is using the hydrodynamic model, but in a, it's a spam. I get that every day at this time. So it is, I checked it. It wasn't just an assumption. So this is starting with a really disturbed flame. You put different Fourier modes, and you see what happened in time, and you see that when you were above the critical value, maximum length large, it flattened out, but otherwise it get, you know, this shape. Even in 3D, it pointing toward the burn gas as expected. And of course, there's a difference in the propagation speed of the cusp-like between 2D and 3D. Remember this because I will say something about it in the next lecture. This is the last slide here. It shows that variation of Marx, and then will give rise to flames with sharper cusp. By the way, this is done on a box, square box. So of course, the origin of these tent-like is related to the box size and so on. If you do it in 2D, it becomes only one, and it's clear. And you can play with that if you're interested. We didn't. So I think, oh, there's even one with circular flames. It showed that in fact, here they get created very early on. Note that also the shape of the flame has this Dario-Landau effect, which is pointing towards the burn gas. But as you proceed, then there will be a tendency of, I don't know if I'll describe it, I maybe shorten my talk here, but what you can see is that large cells split into smaller cells, and two small cells. Remember I told you when we're looking at the hyperbola, there is like a minimum size of those small cells. So when they become too small, they start merging. And so you get small cells merging, large cells, they're too large, they split. And you can explain the splitting because a large cell, it's like a section of a spherical flame. And the spherical flame becomes unstable when it reaches a certain radius. So when that cell reaches certain size, it's split. So anyway, it's interesting. This behavior was observed experimentally, in other words, and it's totally related to cell splitting and merging. The people that have observed that called it a pulsation or oscillation. It's not really an oscillation. It's not monotonic in time, but it's due to cell splitting. And the reason we know that, whereas experimentally it's hard to tell, is because we can focus on the calculation at a given time and move short time thereafter and try to understand what happened between one time and another. It's not something you can do in the lab. Thank you.